Okay, May, June 2022, paper 6, variant 1. Yeah. Question 1. We're investigating the stretching of a spring. We have the following apparatus. And on figure 1.1, take two readings from the meter ruler to determine the unstretched length L note of the coiled part of the spring. We need to take two readings from the meter ruler. What are the two readings? Reading 1 and reading 2. How can I find reading 1 and reading 2? Okay. To find the original length of the spring, we need distance from the top of the spring to the bottom of the spring without the hook. Why? Because the hook doesn't extend. Because the hook doesn't extend. So the top reading would be around 21 point, I guess, point 3. Okay, this would be the top reading, 21.3. And the bottom reading would be around somewhere, yeah, this would be the bottom reading, okay, which is around 22.8. This is the readings. Now, these are the readings we take for the spring. And to find the original length, all you do is subtract 22.8 minus 21.3, 22.8 minus 21.3, which gives you 1.5 centimeters. This is the original length of the spring. And draw a diagram to show clearly how you would use a set square to obtain an accurate reading from the meter ruler. Set square, which is the triangle. Okay, we need to see how can we use this triangle to obtain an accurate reading from this meter ruler. Basically, we can use the ruler. Okay, we need the ruler to be close to the spring, so we can draw the spring. Okay. And then we can add the ruler from one side, for example. Okay, so this is my ruler. We have the readings on the ruler, and then you can just put the set square on the other side or whatever. The set square needs to be perpendicular to the ruler. Okay, needs to be perpendicular to the ruler, and that's it. Okay. You need to draw the set square perpendicular to the ruler. Why? Because all you do is, this is the set square, all you do is just take the reading from the bottom, or you can take the reading perpendicularly to avoid the parallax error. Okay? Avoiding the parallax error. Yeah. Uh, the student suspends a load of P1 Newton from the spring. He records the new length, L1. Calculate the extension. Can I find the extension? Yes, you have L1 and L note. L1 is 2.2 minus L note, which was 1.5. 2.2 minus 1.5 is 0.7. Can I calculate K? P. K equals P over E1. Yes, you have P, and you have E1. P is 1 newtons. And E1 is 0.7, so 1 over 0.7. 1 over 0.7, which is 1.43. 1.43. He said include the unit. Include the unit. Do I need to memorize the unit of the K? No, you don't need to memorize the unit of the K. What is the unit of P? P is newtons. What is the unit of E1? Centimeters. So newtons per centimeter. Newtons per centimeter. No, piece of cake. So. He suspends a load of P5 newtons and the length is now 6.3. Can I find E5? Yes, I can find E5, which is L minus L note. Again, 6.3 minus 1.5. 6.3 minus 1.5 is 4.8. 4.8. Can I find the new K? Yes, I can find the new K. Okay, now P has changed. P has changed. P is now 5 newtons and E5 is 4.8. So 5 over 4.8. 5 over 4.8 is what? Let's calculate it using the calculator. 5 divided by 4.8 is around 1.04. So the new K is 1.04. Again, I can include but he said give your answer to two significant figures. Two significant figures. So if you actually write 1.04, this would be wrong. It would be wrong. It needs to be 1.0. Needs to be 1.0. So I should write K equals 1.0 newtons per centimeter. Newtons per centimeter. So now we have two values of K. Now we have two values of K. I guess that the next question would be to determine whether these two values are the same. Yes, state whether your two values of the spring constant K can be considered to be equal or not. Are they equal or not? First K was 1.43. The second K was 1.0. 1.0. Are they equal? I guess not. Why? Because if we divide them, okay, if you use this simple equation, 1.43 divided by 1, which would give you 1.43, meaning that there's a 43% change, which is a significant amount. It is a significant amount. So the statement, are they the same result? No, not the same. Explanation. Numbers or the values are far apart. Values are far apart. And then we need to state whether they are within the limits of experimental accuracy or not. Exceeding the limits of experimental accuracy. Exceeding the limits of experimental accuracy. Okay. A student improves the experiment by taking additional sets of readings. Additional sets of readings suggest the additional apparatus that the student uses. Okay. What are the additional apparatuses that he might use? Well, he needs to take different sets of readings. How can I increase the sets of readings? By increasing the number of loads. So the additional apparatuses that might be needed for this question would be additional loads, because instead of only using 1 Newton and 5 Newtons, I can use 2, 3, 4, and then go above 5, 6, 7, 8. So we need to use additional apparatuses, okay, or additional loads, okay, additional loads. Suggest how the student uses these additional results. How can it's more of a planning an experiment. Okay, if you think about how can I plan this experiment, suggest how can he use these additional results. Now, if I use the 2 newtons, the 3 newtons, the 4 newtons, and then we have several values for the K, how can I compare these results by using a graph? Okay, by using a graph, we can take the average and then draw a graph. Okay, by taking average, and compare using a graph. Okay, additional, not one load, additional loads, several loads. Okay. A student investigates the cooling of water. Cooling of water. The thermometer reads the room temperature theta R. What is theta R? Theta R is 23 degrees Celsius. Again, do not forget the unit. 23 degrees Celsius. Okay, 1, 2, 3. The student pours hot water into the metal can. Complete the column headings. Can I complete the column headings? Yes, the time is every 30 seconds. So time is in seconds. Okay, the theta is in degrees Celsius. Degrees Celsius, yes. Exactly. The student pours water and the volume of the water is 196 centimeters cubed. Suggest two precautions taken when reading the volume of water. What are the two main precautions while taking any reading from the cylinder, from the measuring cylinder? The two main precautions are to take the reading perpendicularly. Why? To avoid the parallax error, and also to take the reading from the bottom of the meniscus. Okay, two main precautions while dealing with a measuring cylinder. Taking the reading perpendicularly. Take the reading perpendicularly to avoid parallax error. To avoid, yeah, to avoid the parallax error. Also, you need to take the reading from the bottom of the meniscus. Take the reading from the bottom of the meniscus. Okay. The student records the volume V to the nearest 1 centimeter cubed. Suggest why this is appropriate. If the reading, for example, wasn't exactly 196, okay, if the reading wasn't exactly 196, why would it be appropriate to take it to 100? If it was 196.3, why would it be appropriate to just to say 196? Okay, because actually measuring cylinders, most of the measuring cylinders can't measure that accurately. Most of the measuring cylinders cannot say to a very good extent it's exactly 196 point whatever. Okay, most measuring cylinders only take readings every 1 centimeter cubed. Okay, most measuring cylinders. Okay, cylinders only measure every 1 centimeter cubed. Can I find the decrease in temperature delta theta 1 between 0 and 60 and then find the rate? Yes, I can do that. Between 0 and 60, 0 was 84, 60 was 75. 84 minus 75, 84 minus 75, which is 9 degrees Celsius. Huh. Can I find delta theta 1? Yes, 9 over 60. 9 over 60 would give you 0.15. And then do not forget the unit. 0.15. 0.15. The unit would be degrees Celsius per second. Yes. Degrees Celsius per second. Then, can I find delta theta 2 between 120 and 180? Yes, between 180, 120 and 180, it was 70 to 67. 70 minus 67, which is 3 degrees Celsius. Can I find R2? Yes, I can find R2. 3 divided by 60. 3 divided by 60 would be 0.05. Again, if I include the unit, it would be degrees Celsius per second. And we can see that the rate of cooling has definitely decreased. Okay, the rate of cooling definitely has decreased, R1 and R2. A student suggests that the rate of cooling is lower when the temperature of the water is lower. So state and explain whether the results support his suggestion. Yes, definitely. Definitely the results suggest or support this suggestion. Why? Because when the temperature was 84, when we started off with 84, the rate was 0.015. But when the temperature was 70, if we think about it, delta theta 1 at time zero, the temperature started at 84 degrees. So in the first 60 seconds, the rate of cooling was 0.15. But when the temperature was 70, which is significantly lower, okay, between 120 and 180, the rate of cooling was 0.05. So definitely the rate of cooling has decreased. Okay, you can include these numbers in your answer. So yes, okay, when let's write it down. Okay, when the temperature was 80 degrees, okay, the rate was 0.15 degrees Celsius per second. But when the temperature, okay, the starting temperature was 80 or 84. It was 84. Okay, let's write it down. 84, not 80. 84. But when the temperature was 70, the rate of cooling, the rate was 0.05 degrees Celsius per second. Okay. The student states that most of the thermal energy lost by the water in the can is by evaporation from the surface of the water. Okay. One of them is saying it's by evaporation. Another student is saying that most of the thermal energy is lost by the conduction through the sides of the can. Okay, through the sides of the can. Suggest one suitable addition to the apparatus for each additional apparatus. How can I add some apparatus or whatever to state whether these suggestions were correct or not? As for the evaporation, how can I try to reduce the thermal energy lost by evaporation by using what? Definitely by using a lid. We need to cover it using a lid. So first of all, you can use a lid. Okay, how can I prevent or not prevent, decrease the energy lost by conduction? Okay, through the surfaces of this can. How can I? By using some insulation. By using some, you can cover. Okay, you can cover the can with whatever type of insulating material, with plastic, with wood, with wool, with cotton, with whatever insulating material. So we can use an insulating material. Okay, moving on to the next question. A student investigates the resistance of a wire. Okay, in A, the student measures the current and decides that he wants to use a lower current. Okay, he wants to change the current. He adds a variable resistor to the circuit. A variable resistor. On figure 3.1, mark with an X a suitable position for this variable resistor. A suitable position for this variable resistor would be probably on this side. Would it be wrong if I draw it here? No, it wouldn't be wrong. Would it be wrong if I draw it here? No. Again, but the most suitable position would be probably at this position. Okay. The student measures the current I in the circuit. Record the current shown in figure 3.2. Can I see the current? It's almost zero point 0.4. It's almost zero point 0.4. It's exactly what? 0.38. 0.38. Again, do not forget the unit, which is amperes. If you ever know a unit, okay, if you're sure that you know some unit, write it down. If you're not sure that you know the unit, do not write it down. But you have to know the unit for the current, the voltage, the length, the time, the rate of cooling. Okay, so these are all some and resistance. Definitely, we need to know the unit of the resistance. Okay, so you just need to write down any unit you know of. The student places the sliding contact at a distance of 85 centimeters from B. 85 centimeters from B. So the distance from B all the way to sliding contact S is now 85 centimeters. And he records the potential difference using the voltmeter. The potential difference in this question is 2.6. Record the potential difference in the table. Okay, so the potential difference in this table would be 2.6. Can I find R equals V over I? Yes, I can find R equals V over I because you have the resistance, you have the voltage 2.6, and the current was 0.38. Current was 0.38. So the resistance would be around 6.84. Okay. Can I complete the column headings? Yes, I can complete the column headings. Again, the voltage is in volts, V. The resistance is in ohms. So you have the column headings. Plot a graph and start both axes at the origin. So plot a graph of R on the y-axis. R on the y-axis, okay? R slash ohms on the y-axis. L slash centimeters, okay? L slash centimeters on the x-axis. Okay, I'll start from the origin. I need to go up all the way to 6.84, so I guess it would be a bit suitable to increment by 2s, 2, 4, 6, 8. And then the length, it would be suitable to increment 20, 40, 60, 80. Yes, 20, 40, 60, 80, and 100. Let's zoom in and draw or plot the points. First of all, 5 and 0.53. 5 and 0.53. Where is 5? Okay, so this is 10. Okay, 5 would be in the center. 0.53, this is 1. So 0.53 would be around here. So this is 5 and 0.53. Again, we're plotting using very small x's. Um, 25 and 2.11. 25. Okay, so this is 30 and 25. This is 25 and 2.33, 2.2, 2.4. So it's in the middle. So this would be 2.33. Um, 2.33. Again, 45 and 3.68. 45 and 3.7, you can say. 45 and 3.7. So this is 45. 3.7 is, this is 3.6. 3.7. So this is 3.7. Hmm. Okay. 65 and 5.26. 5.3, you can say. 65 is that? Yeah, 65 and 5.26. 65. So this is 65 and 5.26. 5.26, 5.3. Yes. Um, 85 and 6.84. 85 and 6.84, which would be around here. This would be 6.84. 6.84. Can I draw um, the line of best fit? Yes, definitely I can draw the line of best fit. Okay, the line of best fit definitely doesn't have to go through all of the points. Definitely does not need to go through all of the points. Okay, so let me draw the line of best fit in this question. Line of best fit would look somewhat like this. Okay, let me use a different color. Let's use blue. Okay, I like blue. And then if we draw a line of best fit, it would be somewhat like this. Okay, now, this is an okay line of best fit. It's an okay line of best fit. Not bad. Um, yeah. Can I find R? Can I find R, the resistance of the wire? Okay, when the length was 50 centimeters, yes, I can find the resistance of the wire when the length was 50 centimeters. Where was 50 centimeters? 50 centimeters was, let's use another color, okay? Let's again go with blue. So this is 50. At 50, can I draw a line? Yes, I can draw a line using the ruler, okay? To hit this line of best fit, and then we can draw another line, okay? It should be straight, which is 4.2, okay? Should be around 4.2. Definitely there's a range, so don't worry. It's around 4.1, 4.2. Okay, I guess you can go up to 4.3. So it's within this range. So the line of best fit for this question would be 4.2 ohms. Okay, hmm. Yeah, let me remove this line and let's move on to the last question. I guess this drawing was a bit easy, wasn't it? Okay. Last but not least, the planning and investigation. The student investigates the force required to break different beams made from a mixture of sand and cement. Mixture of sand and cement. Plan experiment to investigate. Plan experiment. to investigate the force required to break the beams. The force required to break the beams. So we have different beams made from a mixture of sand and cement. All of the beams have the same cross section. They all have the same length. Okay, what should we do? What should we do? Actually, this question might look a bit tricky, but it's not that tricky. All you're doing is what? You're changing the mixture. You're changing the mixture of sand and cement. So basically, you have a ratio of sand and cement, for example, 1 to 1, or 1 to 1.5, or 1 to 2, or whatever. Okay, so you're just changing the ratio of sand and cement inside the beam, and you need to see whether these loads will break these beams or not. Okay, you need to see whether these loads will break the beams or not. Or, okay, um, let's check out the remaining of the questions, the remainder of the question. Okay, the following apparatus is available. A selection of beams made from different ratios. Okay, so we have different ratios. A triangular block to support the beams, these pivots, if you might say. A meter ruler, a selection of loads. You can use other apparatus and materials that are usually available in a school laboratory. The student takes all of the necessary safety precautions. You're not required to talk about safety precautions. So for this question, you do not need to write any precautions. In your plan, you should explain how you would carry out the investigation, state the key variables, draw a table, and explain how you would use the readings to reach a conclusion. Okay, so what should I do? What should I do? Should I plan the experiment to see whether the ratios, okay, see the ratios, the selection of ratios, whether these ratios would break the beam or not, or if these ratios would affect the strength of the beam or not, or should I see whether, for example, the loads, okay, whether the loads, if I increase the loads, will they break the beam or not, okay? Um, Either or, actually. You could use either or. One of them, if you use one of them as the range of values, if you use one of them as the independent variable, then the other one would be one of the controlled variables. Okay? So you either say that I will change the ratio. Okay, it might be a bit difficult to say I'm changing the ratio. Can I say, for example, I will change the distance, okay, distance between these two pivots, these two triangular blocks? You can, okay, you can do that. Why can I do that? Because if you change the distance and you add the load in the center, if you change the distance and you add the load in the center, what would happen? If you increase the distance, the beam might actually break easier. The beam might break easier. If you increase the distance, and if you decrease the distance, it would be a bit more stronger. Okay, so let's go on. Let's go on with this suggestion. Okay, that I will change the distance between these two triangular blocks, if the distance is 10 centimeters, can I keep on increasing the distance between these two beams, these two triangular blocks? Yes, I can. What about the ratio? What about the ratio of sand? Can I keep the ratio constant? Can I keep the ratio constant? Yes, you can keep the ratio constant. Okay, so this is one of the key variables. So let's go on. Let's write down the steps. What are the steps? First of all, you need to write down the range of values. Range of values. What is the independent variable? Independent variable in this question would be the distance, okay? The distance between the two triangular blocks. Distance between, okay, between the two triangular blocks. Would it be okay if I said the ratio of the sand to the cement? Yes, it would be. It would be okay. So if I say the distance between the two triangular blocks, can I state different values for the distances? Yes, definitely. I need to say some suitable values for the distances. For example, if I go on and say 5 centimeters, 10 centimeters, 15, 20 centimeters, 25 centimeters. Okay, so I have different distances for the You have different values for the distances between these two triangular blocks. These are the range of values. What about the next point? You need to write down the controlled variables. What are the controlled variables? Controlled variables. For this question, you need to write down one of the controlled variables as the ratio, of the ratio of the sand to the cement. Okay, you need to write down the let's say the position at which you add the load. For example, if you want to add the load exactly in the center of this beam, okay, if you want to add it slightly to the left or slightly to the right, whatever, but the position needs to be constant. The length of the beam needs to be constant. The whatever, okay, whatever. So let's write it down. So first of all, you need to say the ratio, okay, of sand to cement. You need to say the position of the load on the beam, the length of the beam, okay, the length of the beam, and yeah, that might be enough. If you say the cross-sectional area of the beam, okay, it would be okay. Controlled variables, okay. We don't need to write any additional apparatuses. Why? Because we've already got all the apparatuses needed. Okay. State the key variables. Okay. Can I write down the steps? Yes, I can write down the steps. Explain how will I conduct this experiment. Okay. As for the steps, what should I do? Okay. I need to see whether it would break or not. Whether it would break or not. So what should I do? I should just add the load, okay, and keep on increasing the loads added until it breaks. Until it breaks. That's it. So add the loads, okay, add the loads on the beam. And then add the loads on the beam, increase the loads until, okay, it breaks. Then repeat the experiment. Okay, repeat for several beams. You can repeat for several beams. That's it. We don't need to go into too much details because it's a new experiment. Okay, this is one of the newer experiments. We haven't thought about this experiment before. So when he gives you new experiments, new ideas, he doesn't actually expect you to go into too much details while thinking about this very difficult. It's not difficult, but this is very new experiment. Okay. Can I draw a table? Yes, definitely I can draw a table. Okay, the table wouldn't have that much actually. The table wouldn't have that much. Why? Because all you're doing is what? Changing the distance and checking the loads for which it will break. That's it. So I can write down the distance and the load. Can I draw the table in this empty space? Yes. Okay. Distance, okay, definitely. It would be better if you use a ruler to draw the table. Okay, it would be better. You have the distance in centimeters, and then you have the load in newtons. That's it. That's it. Can I draw a conclusion? Yes, I can draw a conclusion. Can I draw a conclusion? What is the conclusion? How can I reach this conclusion? First of all, how can I reach this conclusion? For each distance between the two triangular blocks, for each distance, for each distance between the two triangular blocks, two triangular blocks, blocks. Repeat the experiment and take average. Repeat the experiment and take average. Then when you repeat these experiments, what should I do? What should I do after I repeat them? You should include this value. Okay, you should record these values in the table. Okay, record these values in the table. In the table, and then we can compare the values for which. Okay, we can compare the values for which the beams break, for which the beams break. You can draw a graph, for example. You can draw a graph. That's all you need to do. That's all you need to do for this question. 7 very easy marks. Okay.